Hi there. Welcome to this lesson on Further Pure Mathematics 2. We're on chapter 1 that deals with inequalities, and in this lesson we'll be looking at graphical solutions of inequalities, in particular inequalities that involve algebraic fractions. How do we do that? Well, the method's extremely similar to how you solve simultaneous equations graphically. If you had y equals f of x and y equals g of x, and you wanted to solve those equations simultaneously, then you're finding where f of x equals g of x. We'd sketch the two graphs, we'd sketch f of x, we'd sketch g of x, and then we just find where the two graphs cross each other. If we have the inequality, f of x is greater than g of x, same thing. We sketch f of x, we sketch g of x, we find where the two graphs cross, and then there's just one final step. We give the range of values for which f of x is greater than g of x, which is where it's above it on the graph. Okay, we'll have a look at an example. Solve graphically, the inequality 7x over 3x plus 1 is less than 4 minus x. Now, before we start, I should say it's very, very tempting just to multiply through by 3x plus 1 here. But don't be tempted. When you multiply through by 3x plus 1, it feels like you simplify the question greatly. You end up with a quadratic, and it's just 3x squared minus 4x minus 4 is less than 0. That is very easy to sketch, and it's very easy to show when it's less than 0. The reason why you can't do that is because we have an inequality. And multiplying by an algebraic expression like 3x plus 1 is problematic because it depends on whether 3x plus 1 is positive or negative. And we don't know. It'll be different things for different values of x. But if it's less than 0, if it's negative, then we would have to change the sign of this inequality. Better to avoid those issues altogether. So rather than doing that, we do just sketch the two separate functions. We sketch f of x equals 7x over 3x plus 1. Then we sketch g of x equals 4 minus x. Once we've done that, we find where the two graphs cross each other. And once we've done that, we write down the range of values for which f of x is less than g of x when it's underneath it on the graph. Now, if you'd like to have a go yourself first, feel free. It's this first sketch which is the difficult one, but if you'd like to have a go at sketching it, then do. And come back to me when you're ready, and we'll go through the whole thing in detail. Okay, we'll have a look at this together. Now, as I said, sketching rational functions, it's just a little bit tricky, it takes a bit of effort. There is a standard method for doing a sketch of a graph for any strange function where you're not quite sure exactly what it looks like. And I would always follow this order. So where possible, first of all, find where the y-axis crossing points are. Once you've done that, find the x-axis crossing points. Once you've done that, see if there are any turning points. Sometimes it's very difficult to find that out, but if it is easy, find out if there's any maximum points or minimum points on the curve. Then go looking for asymptotes. So see if you can find any vertical asymptotes. And if you do find an asymptote, you'll need to check what happens either side of the asymptote. So what happens as the curve approaches the asymptote, both from beneath it and from above it. And then lastly, check what happens as the curve heads into the far distance, as it heads to the right-hand side and plus infinity, and as it heads to the left-hand side and minus infinity. Okay, we'll go through those in order for this question. Find the y-axis crossing points. The reason why you do that first is it's nearly always very easy to do. All you're doing is saying what happens if x equals 0, and that'll give you the y-axis crossing points. Well, if x equals 0, f of x will equal 0 divided by 1, which just equals 0. And that means there's a crossing point on the y-axis at 0, 0, at the origin. That point will lie on the curve. Slightly more tricky normally is finding the x-axis crossing points, which are the points where f of x or where y equals 0. Now, if f of x equals 0, That'll give us 0 equals 7x divided by 3x plus 1. That gives us 7x equals 0, and that only has the one solution, x equals 0 again. And that's the same point that we found just now. So 0, 0 is the only crossing point on either axis. So the x and the y axes are only crossed once, and that is at the origin. At this point, I would start doing the sketch and just gradually fill in the details as we work through those 6 steps. So that's what we just found. We know that 0, 0, the origin, it's the only crossing point on either of the axes. The third step was to try and find any turning points. Now, reciprocal curves like this, algebraic fractions where you've just got a linear term here, a linear term here, they don't tend to have any turning points at all. And this one doesn't. It has no maximum points, it has no minimum points. If you wanted to prove that was the case, it's not that hard. You differentiate this function, let the differential equal 0, and quickly you find out you get an equation that has no solutions, and there aren't any turning points. So no maximums, no minimums. That'll be significant later on. It doesn't have any. Then go looking for asymptotes, vertical asymptotes anyway. And vertical asymptotes will happen where the bottom of the fraction, the denominator, is equal to 0. So if 3x plus 1 is equal to 0. Well, that will happen on one occasion when x equals minus a third. So there will be a vertical asymptote which cuts through the x-axis at x equals minus a third, and we'll sketch that now. So green dotted line there is a line that the curve can never touch, it can never cross. It can approach it, but it can't touch or cross it. Horizontal asymptotes are important as well, but we'll find those later on. We find those normally, in fact probably always, when we check what happens as x tends towards plus or minus infinity. But before we do that, we need to go back to the asymptote at minus a third and just find out what happens as the curve approaches it. Now, what we'll do first of all is say what happens as the curve approaches from the left-hand side, from below, from beneath. And the normal way of writing that is what we have here. This says as x tends towards minus a third from below. That's what the minus there means. But what does the function do as x gets closer and closer and closer to minus a third from below? Well, if it's a bit less than minus a third, on the bottom of this fraction, you'll have 3 times a number which is a bit less than minus a third. When you add 1 to that, you'll get something very close to 0, but it will be negative. So it'll get closer and closer and closer to 0, but the significant thing is the negative here. On the top, as x tends towards minus a third, well, the top just tends towards minus 7/3, 7 times by x. But it's the bottom thing that you need to be careful with. The bottom is going to head towards 0 because we've got an asymptote. What you need to check is whether that's going to be plus or minus 0. In this case, it would be minus 0. So a negative number very close to 0. When we divide by 0, we'll get infinity. The minus matters because we've got a minus divided by a minus. Minus divided by a minus will give us a plus, and that means that the function is going to head towards plus infinity as x tends towards minus a third from below. And at this point, what I would do is I would just sketch that little bit on the graph. So up here, we've got a line because as x goes towards minus a third from below, the function's heading up. It's heading up towards plus infinity. Now we do the same thing looking at the other side of the asymptote. So what happens as x tends towards minus a third from above? That's what the plus there means. What does the function do? Well, on the top, you'll still just get minus 7/3 as x gets closer and closer to minus a third. On the bottom, this time, it's going to be 0. But if you're a little bit above minus a third, what you will get is a positive number, closer and closer to 0. If ever you're not sure about this, just put in a real number which is a tiny bit bigger than minus a third. And just check, is it positive? is it negative? It matters because we've got a minus divided by a positive. Dividing by 0 would give us infinity, and a minus divided by a positive means that the function is going to tend towards minus infinity. Then we'll sketch this on the curve, and sketching it on the curve gives us a black line down here. As x tends towards the asymptote from above, the function tends down and down and down towards minus infinity. Okay, number 6, we ask what happens in the far distance. So as the curve heads towards the right, towards plus infinity, as the curve heads towards the left, towards minus infinity. First of all, we'll look at plus infinity. As x just gets bigger and bigger and bigger, what happens to the function? Well, the function will tend towards 7x over 3x. The 1 becomes trivial. So if you have a really, really large number for x, then the 1 makes very little difference. So the function will just tend towards 7x over 3x. You can cancel the x's. And that means that as x tends towards plus infinity, the function is going to tend towards 7/3. We'll check what happens for minus infinity. Normally you get exactly the same thing. As x tends towards minus infinity, again, the function will just tend towards 7x over 3x. It'll be a minus over a minus, but they'll cancel to give you a plus. And again, the plus 1 becomes trivial. So exactly the same thing happens. You can cancel the x's, and the function will tend towards 7/3 as x tends towards minus infinity. So in both directions, as x gets bigger and bigger, the function is tending towards a limit. That means we'll get a horizontal asymptote at 7/3, at y equals 7/3, or f of x equals 7/3. So there we have sketched it onto the graph. At 7/3, there's a horizontal asymptote. And as the curve gets bigger, it's going to tend towards that asymptote. As the curve tends towards minus infinity, it'll also tend towards that asymptote. We need to check which side it tends to. And you can't assume that it's going to go to one side or the other. Sometimes these things do actually cross over the asymptote and then come back towards it again. So you do need to check. So first of all, what happens as x tends towards plus infinity? Well, that's what we've already said. The function tends towards 7/3. But now we need to think in a little bit more detail. That plus 1, we've said it becomes less and less important, but it does exist. So that plus 1 is always there, which means on the bottom, you'll always have something which is a tiny bit bigger than 3x. So this will be a tiny bit bigger than 3, which means when you divide by it, you'll actually get something which is less than 7/3. The consequence of that is we need this minus here. So as x tends towards plus infinity, the function does tend towards 7/3, but from below, from beneath it, it'll always be a little bit less than 7/3 because of this 1. Putting that on the graph, we'll just draw a little black line here that shows as x is tending towards plus infinity, the function is tending towards the asymptote from beneath, from underneath the asymptote. We'll do the same thing for minus infinity. Now, if you have minus infinity, when you have minus a very large number and you add 1 to it, it'll become a bit smaller, which means rather than tending towards 7/3, you'll actually have something which is a little bit bigger than 7/3. Again, if you're not sure that this is true, just try with real numbers and check. And you'll see that the answer is just a little bit bigger than 7/3 all of the time. So that means we need to put a plus there. And then you'd read this as saying, as x tends towards minus infinity, the function tends towards 7/3 from above. That's what the plus means. Putting that on the sketch means we'll get a black line here. That's where the curve is going to head towards. Now, that is all the detail that we can find out and all the detail that we need to find out. At this point, you can start joining things together. The asymptotes never get crossed, so don't be tempted, or certainly the green one doesn't. The vertical asymptote, it's impossible to cross. Horizontal asymptotes actually are a little bit more complex, and they can be crossed. But looking at the right-hand side of the green asymptote, you've got a curve that starts here. We know it's going to cross the origin. We know it's going to end up here. And we know that there are no turning points. So nothing strange happens. There are no maximums, no minimums. We can draw this right-hand half now. It'll look something like that. And the left-hand half is very straightforward. It starts here, it finishes there. Again, nothing strange in the middle. No turning points, no maximums, no minimums. It will look like that. Finally, we should give it a label. So what we've drawn there is f of x equals 7x over 4 minus x. And again, note it is a sketch. We haven't drawn accurate axes. We haven't drawn accurate scales. We've just shown the key points that matter. The next thing to do is sketch g of x equals 4 minus x. This is a lot more straightforward. It's just a straight line. The same process does work, by the way. You just use the first two steps with a straight line. So step one is saying, where does it cross the y-axis? Well, that's where x equals 0. If x equals 0, we'll just have y equals 4, or g of x equals 4. And if y equals 0, then 0 equals 4 minus x, and you'll get x equals 4. So two crossing points, one at 0, 4, one at 4, 0. That will be here and here. Then we can draw the line. It'll cut through both of those. Then we'll give it a label. So there we have g of x equals 4 minus x. Now the next step, find the crossing points of the two graphs. So for me, it's where the red graph cuts the grey graph, where 7x over 4 minus x cuts through 4 minus x. Well, you can see it happens at these 2 points here, one there and one there. And we need to find the x values of those 2 points. I'll find the y values as well, but strictly speaking, it is only the x values that we need. How do we do that? Well, we just solve like we normally would do if you were solving two simultaneous equations graphically. So we solve 7x over 3x plus 1 equals 4 minus x. When does the one curve equal the other curve? Moving the 3x plus 1 to the other side, you get that. Multiplying at the brackets and collecting up terms, you get a quadratic. 3x squared minus 4x minus 4 equals 0. That does factorize into 3x plus 2 times x minus 2 equals 0. And that gives us two solutions, either x equals 2 or x equals minus 2/3. Because it's so easy to find the y values, I have done. To find the y values, I just use g of x equals 4 minus x and put the two x values into there. And that gives us the coordinates of the two crossing points. 2, 2, that's this one over here, and minus 2/3, 4 and 2/3. That's the one on the left-hand side. So just to complete the graph, I'll write in those coordinates as well. Okay, we've very nearly finished. That was the question. Solve graphically the inequality. 7x over 3x plus 1 is less than 4 minus x. Step one was sketching the two functions. That we have done. Then we had to find the crossing points of the two graphs. That we have done. And then the final thing is write down the range of values for which f of x is less than g of x, for which 7x over 3x plus 1 is less than 4 minus x. Well, that's when the red curve is beneath the grey straight line. So it's underneath it, it's less than it, all the way up to this crossing point, all the way up to minus 2/3. And then it's less than it again once you get beyond minus 1/3 and head up towards 2. So there's two ranges, up to minus 2/3 and between minus 1/3 and 2. The red curve is underneath the grey straight line. So we'll write down the answer, and that is it. 7x over 3x plus 1 is less than 4 minus x if x is less than minus 2/3, or if x is between minus 1/3 and plus 2. Okay, that gets us to the end of this lesson. If you do have the textbook, then turn to page 7 and have a go at exercise 1b. Thank you very much for listening, and cheerio.